So far, we have only been talking about statistical significance. This refers to comparing the p-value to the alpha level. If your p-value is less than the alpha level, then you have statistical significance, and you have support for your research hypothesis. Now, statistical significance is really important, but it only tells you one part of the story. You also should look at practical significance. If you have statistical significance, that just means that you're able to detect a difference, but you want to know if this is actually a big difference or not. And that's what practical significance tells you. So remember in our example, the claim was that the average time was 30 minutes, and we found that a sample average of 31 minutes was statistically significant. However, is 1 minute that big of a deal? Probably not. 1 minute is probably not going to be that big of a deal unless you're really, really hungry. Then maybe it would be a big deal, but most of the time, probably not. So in this case, we found statistical significance, but there wasn't really practical significance because that 1 minute difference that we found is not that big of a deal. Now, if it was 20 minutes, then there would be practical significance as well. So with the minute example, we could just tell by looking at the difference if there was practical significance. Because minutes for pizza delivery times is kind of easy to assess if it's a big difference or not. 1 minute, not very big. 20 minutes, yeah. But what if the units aren't as interpretable? So say we have a customer satisfaction scale from 1 to 10. And the pizza place claims that the average is 8 out of 10. But you think it's less than that, so you take a sample and you find a mean of 7. Is that a big difference? 7 to 8. Is that really a big difference? Well, it's kind of hard to tell at first. It kind of depends on the standard deviation. So the difference of 1 on a scale from 1 to 10 might not be a big difference if the standard deviation is 4. But maybe it is a big difference if the standard deviation is 0.2. And that's what Cohen's d considers. It considers the difference and the standard deviation. So I'll give you another example. If you're comparing heights and you found a difference of 1 inch, and that was for adults, maybe men and women, 1 inch is not that big of a deal. A little bit, but it's not that much for adults. But if you had 1 inch for babies, that's a lot bigger deal. And the reason is because there's different standard deviations. For adults, because you're higher or you're taller, you also tend to have a higher standard deviation. But for babies, because they're smaller, they have a smaller standard deviation. So it just kind of depends on what is a big difference, and a way to assess that is through looking at the standard deviation. And Cohen's d is a measure of practical significance that's useful when the units are not as concrete, such as Likert type scales, and you don't really know what a 1 means on the scale. It's kind of abstract. So we can use Cohen's d. You can use Cohen's d if the units are abstract or not abstract, it doesn't matter, but they're more useful when the units are kind of abstract, like a Likert type scale. Here is the formula. D equals the sample mean minus the population mean from the null divided by the standard deviation. Notice we divide by the standard deviation and not the standard error. The standard error depends on the sample size and will get smaller and smaller as the sample size increases. A small difference might be detected if the sample size is large enough. So even though the difference was only 1 in our example, because we had a large enough sample size of 100, we found a statistically significant result. But that 1 minute really wasn't a big deal. But you should note that Cohen's d is only helpful to assess practical significance after you find statistical significance. So if you don't find statistical significance, then practical significance, looking at Cohen's d, isn't really worth anything, because if you don't find statistical significance, then maybe that practical significance, if it was big, it could have just been by chance. Because if you have a really small sample size, then that sample mean might be distorted by an outlier. And it's really hard to tell if that mean's really that accurate if you don't have statistical significance. So on a homework or whatever, still find out if there's practical significance, even if there's not statistical significance, but you shouldn't put as much weight on the practical significance if you don't find statistical significance first. Here's an example. This is from our delivery time example. So we have 31 minus 30 divided by 5, and we get 1 over 5, which is 0.2. And I'm just comparing this to the z that we found, or the t. And you notice that in the bottom, instead of just 5, we have 5 divided by the square root of 100, because this is a standard error here. And that ends up being 0.5 for the standard error, and so we have 1 divided by 0.5, which equals 2. So notice the 2 leads to statistical significance, but the 0.2 is somewhat small for practical significance. So we find a difference, but the difference isn't that big. Here's another example. So the average height of women is 64 inches, and the average height of men is 70 inches. We can pretend that the women's mean is from a sample, and the men's mean is population mean. And the standard deviation for height is around 3 inches. So this is how you would calculate the Cohen's d. So 64 minus 70 divided by 3. And that equals negative 6 divided by 3 equals negative 2. Now this is a much larger Cohen's d. And here is a depiction of the distribution. So in blue we have the men, and in red we have the women. And you can see that even though there's a big Cohen's d, this is a really big Cohen's d actually for psychology, that there's still overlap. This gray area here, still overlapping. So what that means that even though there's an average difference for men and women, it doesn't mean that one particular woman can't be taller than a particular man. So it doesn't mean that, oh, every time you have a man and a woman that the man's going to be taller. Just on average, the men will be taller. And, you can see this pretty clearly if you look around at people, that men are generally taller. And this is a really big Cohen's d, but you still see that there is overlap. But usually in psychology, there's not such a big noticeable difference. You can't really see it as easily as the height difference. So here's some kind of more reasonable Cohen's d's for psychology, at least. In other disciplines, it might be totally different. So 0.2 is pretty small, and that's this first one over here. And we have a lot of overlap, and it overlaps by 85%. So 85% of the distributions are overlapping. So this would be like if the woman's height was still 64, but the men's height was 64.6. And then a 0.5 would be a medium effect size in psychology, and the overlap would be 66%. And if it was 0.8, this would be a large effect size, and the overlap would be 53%. Now, this can be negative or positive. You ignore the sign when you are seeing if it's small, medium, or large, so just ignore the sign. So this is absolute value of the Cohen's d. And, if it's between 0 and, if the absolute value is between 0 and 0.2, you can say that's small. If it's between 0.2 to 0.5, you can say small to medium. 0.5 to 0.8 can be medium to large, and above 0.8 is large, something like that. This kind of just gives you a reference when you look at the different Cohen's d's that you get in psychology. Right, and that ends this video.